let's start. And it would be great if everyone can interact as much as possible, so it's not just the sound of my own voice. So just what we'll cover today, this is taken from the primary syllabus, and as you can see, there's quite a few points to cover about electricity, magnetism, talking about voltage and all the terms that you need to know, going through a couple of types of circuits that are sort of relevant, and then looking at things like the wheatstone bridge, which you've probably heard of before. And then at the end, I'm talking a bit about electrical hazards and equipment safety, which is something that apparently they like to test you on in the Viva. So we will try and get through all of that as quickly as possible. There is also a few MCQs dotted throughout, so please do shout out the answers. Okay, just starting with some definitions. So definition of battery, I won't go around the circle with these definitions because we've got some MCQs coming up. So battery is essentially a power source that supplies electricity as a direct current. We will be talking later about the difference between direct and alternating current. But this is one of the main sources for the direct current. And that is the little symbol that they use to indicate a battery. And then a resistor is an element of a circuit that we use to oppose electrical current, and it causes a drop in the voltage, which is proportionate to the current flow. And this is the squiggly sign that they use for that. And then transducers are devices that convert one form of energy into another, and there's lots of different types of transducers that we use. These are just some of the symbols that they use for transducers. So an example would be an earphone, which transduces, which converts electrical energy to sound, or a microphone, which does the opposite, sound to electrical energy, etc. So then just going on to what is AC versus DC, obligatory picture of AC DC. I'm afraid that is the most fun part of this talk. So does anyone know what the difference between direct current and alternating current is? Mm-hmm.
Direction and point, so
yeah.
One way and alternating can go
back and forth. Yeah, that's a really good explanation. So essentially, direct current, as we were talking about before with batteries, you have a steady flow of electrons in one direction only. And so, yeah, another source would be a thermocouple, which I think we talked about earlier in the year. I don't fully understand, but yeah, batteries are quite a common example of what direct current is. And then alternating current is what we mostly use for through mains electricity. So it describes the flow of electrons first in one direction and then in the opposite direction. Good. A couple more definitions to go through. So charge, charge is the presence or absence of electrons on a conducting or insulating surface. It's slightly confusing because obviously the presence of electrons means it's negatively charged and the absence means it's positively charged. And it is measured in coulombs. And then current in relation to charge is the flow of electron movement through a conductor or around the surface. So a good metaphor they often use is like a water dam, whereby the water is the charge and the current is the flow of water. And we will go through as well what voltage is in a second in that metaphor. So current is measured in amperes, and essentially electrons flow from a high to a low potential. So they flow from negative to positive. Confusingly, in a conventional diagram, it shows electricity flowing from positive to negative, but actually the electrons flow from negative to positive. But that's just the conventional way of doing it. Cool. So this is the dam kind of metaphor. So the voltage in that metaphor would be the driving force. So sort of the distance, the potential that the water has to flow. That could be described as the voltage, and it's directly proportional to the current. And that's measured in volts. So there is a drop in voltage as the current flows through the circuit. And then this is where I got a little bit confused. I think electromotive force is similar to voltage, but it basically describes the driving force from a battery or from a power source. but it's basically the same as voltage when there's no current flowing. So as you can see on this graph, when you connect a battery to something, it raises the potential to the value of its EMF, and then it slowly goes down as the current flows through. That's probably a little bit. Okay, so Ohm's law is an important concept to kind of get our heads around, and it's the best way to sort of calculate voltage, current, and resistance in relation to each other. Obviously, you can rearrange the equations to calculate any of these in a circuit. So a circuit element that has any resistance will impede the current flow and cause a voltage drop across it. And voltage is sort of synonymous with potential difference. So I'll be using those kind of synonymously just to confuse you even more. So yeah, Ohm's law can apply to individual elements in a circuit or to the whole circuit. And this is just a way in which we could calculate the current. So for this circuit, the voltage is 9 volts here coming out of the battery, and then the resistance across this element is 1 mega ohm, and so the current would be 9 microamps once you put it into this equation. So I'm now going to talk about a couple different types of circuits. So the most simple type would be what we call a series circuit, whereby the elements are all arranged in a single line. And so there's only one path for the current to flow through. And therefore, the current through each element is the same. And the total voltage drop will be divided between each of the resistive elements because they all have to pass through each one of them. So the total resistance would be R1 plus R2 plus R3. And then moving on to a different type of circuit, which is a parallel circuit. And this is a slightly more useful type of circuit because they're arranged in a branched way, which means the current is divided between the elements. And so the current could flow from 1 to 2 to 7 to 8, or 1 to 3 to 6 to 8. And these are sort of termed common points. And so the voltage will drop equally between each of the pathways, if that makes sense. And so with this, it has a slightly different equation, which I'm not going to go into too much detail with. But essentially, as you add more resistors, more parallel resistors, the total resistance actually drops, I guess, because you're sort of splitting the current between each pathway. If that makes sense. This is another way in which you can work out the total resistance of a parallel circuit. Okay, little quiz time. I got this from BBC Bite Size because I found it easiest. So let's start with Laura. Can you tell me what the top left one is?
Which?
Yep. Martin, can you tell me what the next one is?
Battery.
Nearly. So I would have said battery as well, but apparently this is a cell, which is a part of a battery. So you're basically correct. The next one is a battery. Essentially, I think of it as like a muscle. So the cells are like the motor units, and the battery is the muscle. If that makes sense. James, would you like to do the next one along? Oh, there's two James. Sorry. James Collin, would you like to do the one below battery?
Below battery, ammeter.
Oh wait, actually, I think I might have. I think I might be revealing the wrong one.
Below switch is a light bulb.
Well done. Okay, I'm just yeah, there we go. Testing you extra. Andrew? Yes, perfect. And then yes, James is right about the ammeter as well. Okay, I think I've tested you all enough for one day. So this is a resistor. This is a variable resistor, which is just another type. We're going to go through capacitors as well. This is the symbol for that. These two actually we're not going to cover too much. They're more sort of related to like lighting and things. And then you probably do recognize that as like the fuse symbol as well. Cool, well done. So the next section is about resistance, inductance, and capacitance, which are sort of concepts that we need to understand how different circuits work, in particular filtering circuits. So I will try my best to explain each of these concepts. So capacitance is essentially the ability of an object to store electrical charge. And a clinical example of this would be a defibrillator, which is the one that's often used. So capacitance itself as a concept is equal to the charge per unit voltage. So capacitance equals charge divided by voltage. It's measured using farads, but most are measured in microfarads. So a capacitor would be an object that is able to store electrical charge. As we said, a defibrillator would contain a capacitor, which is able to then discharge electricity when you shock someone. But the actual element in the circuit itself is basically a pair of conducting plates, which is separated by a space, filled with an insulator, for example, air, and then charge is stored on the proximal plate. When the current flows into the proximal plate, an equal and opposite charge is induced from the opposite plate, and that allows a current to continue flowing around. But when we connect a battery to a capacitor, essentially, as it becomes saturated, the proximal plate, the rate of rise of the potential decreases. So it's kind of like a negative exponential. So it's still going up, but it kind of is plateauing. And then at the point where it plateaus, the current will stop flowing around the circuit. And that's in a battery. We are going to go on to talk about how AC current will flow through a capacitor in a bit. I know it's a very confusing. I found this very confusing, so I hope I haven't over-explained it too much. Moving on to another element that you can use in a circuit is an inductor. So there is a tendency of any conductor that is carrying a current to essentially create a magnetic field around it, and that induces a voltage that opposes the voltage drop. So this is measured in henries, and this is the symbol that's used, or it's also L, symbol for the inductor. Inductor itself is basically any wire carrying a current that has an associated magnetic field around it. And so the special kind of feature of a coiled wire is that it induces a voltage which opposes the main voltage drop, and that's proportional to the rate of change of the current flowing. That's confusing. But essentially, when a wire is coiled, it creates a magnetic field around it, and that creates a voltage itself, but it's an equal and opposite voltage to the one that's running through the wire. Okay, so now I'm moving on to how AC current would work through each of these elements. So as we said in the capacitor, when it reaches the saturated voltage, it will stop flowing a current through the distal plates. But with an AC current, there's a constant wave. So the changing charge induces the plate, and therefore current continues to flow, and that flow is proportional to the rate of change of voltage. And so a graph that kind of shows the relationship between current and voltage in each of these elements is shown here. So with a capacitor, I think C and C, capacitor is the current waveform leads. So the current waveform is the solid line, and the voltage waveform is the dotted line. And so you can see the shape of the current kind of is mirrored by the voltage later. And then basically it's the opposite for an inductor. So an inductor, you again get the waxing and waning of the induced magnetic field and EMF, and this is proportional to the rate of change of current. And so the voltage waveform leads in an inductor. Can you see my mouse? It kind of makes it easier to point to things. Anyone?
Yeah, we can see it.
You can see the map. Okay, cool. Yeah. So basically, bit of a confusing concept, but I think it's easier just to think capacitor. In a capacitor, the current waveform would lead the voltage waveform. Okay. Right. A few more circuits to talk about, I'm afraid. So these circuits are where we combine all of the elements we've already talked about. So the inductors, the resistors, and the capacitors. And in this RLC circuit, each element will have a voltage drop across it. And these are some equations that I got from e-learning for health, which I don't think they're going to expect us to be able to actually do integration and differentiation. But essentially, this would be how you calculate the voltage drop for each element. And it kind of shows you that obviously in the resistor element, it's just Ohm's law, voltage equals current times resistance. But for a capacitor element, you essentially integrate these two values. And it also incorporates frequency. So we're now talking about AC current, if that makes sense. With the inductor, we differentiate, and then the whole circuit, you can see, produces this very lovely equation, which hurts my brain. But essentially, it acts as a filter. So I mentioned earlier that all of these circuits basically allow us to filter certain signals. And depending on which order you put each element in, will depend on what kind of signals you can filter. So I'm going to go into a bit more detail on that now. So I'm just going to put it all up there. So with these circuits, you can see that there is an output voltage and an input voltage. And essentially, this creates a voltage divider, which allows you to modify the input voltage. And this is a type of bridging circuit, as I was saying before. So on the left, we have a RC circuit where the resistor is first and then the capacitor. And it essentially represents an integration of the input voltage. So you have this square waveform going in, and then once it passes through these elements, you get this waveform. And basically, when the frequency of the input voltage is high, then the ratio of the output voltage to the input voltage is small. And therefore, it will block high frequency signals. So it's a low, and it will allow low frequency signals to pass. So it's a low pass. And then essentially, it's the opposite for a CR circuit, which is the reverse. And it represents a differentiation of the input voltage. So it goes from this square waveform to this kind of waveform. And again, if the opposite is the case, so if the frequency of the signal is low, then the ratio is small and it doesn't allow that frequency to pass. And so to try and put some clinical context on this, an example of this would be an ECG waveform. So we want a certain frequency to go through. And so you would use these elements to determine a certain band of waves of frequencies that you want to allow through. This is just another type of circuit which incorporates the inductor and the resistor, and it's another type of low-pass filter. Let's leave it at that. So putting all these together, as I said before, these can create a tuned circuit which allows all the elements to contribute separately to the resistance. The graphs on the right sort of show that when the frequency is high, when the frequency is at a certain level, the reactance, which is also another word for frequency-dependent resistance, is at its lowest, and so it will allow those signals to pass through. Impedance is another word for a combination of reactance and resistance. I'm not sure if I'm going to be able to explain that any more than that, but we'll move on now. Does anyone have any questions up to now? Because I know I've gone through quite a lot of stuff. So if anyone has any questions, please shout out now. We're going to come up to a knowledge check soon, so I can refresh up on memory. Cool. I'm going to take that as no questions. Okay, great. So this is just a true-false question. So we'll go through each one, and they're all related to the RC and the CR circuits that I was talking about. So statement A, an RC circuit acts as a mathematical differentiator. Is that true or false? Anyone? I know, too bad, I'm not going to be able to tell you before I actually click. Okay, that is false. It's the integrator. 50-50 chance, right? Okay. RC circuits act as a low-pass electronic filter. Anyone remember if it's low-pass or high-pass?
I think it was high pass.
No, sorry. I was about to say you were correct as well. That's why I know these things. So sorry, yeah, the RC is the low pass and the CR is the high pass. So this one is also incorrect because it's the other way around. So the RC is the integrator and the CR is the differentiator. A CR circuit acts as a band pass filter. No, that is incorrect because basically I think you have to combine all of them for it to become a band pass filter. And then finally, CR circuit acts as a high pass filter. That is correct. Okay. I think this is another, this is all true false. So it's just one of the following options, which describes best the current and voltage in a capacitor when it's connected to a battery. So the key term here being a battery. So this is not connected to the mains. This is through DC, so direct current. So when a battery is connected to a capacitor, does the current rise as the voltage falls? Does the current fall to zero when the voltage reaches maximum? Does the voltage rise to a maximum then fall to zero? Does the voltage and current rise and fall alternately? Or does the voltage and current remain constant? Does anyone know the answer? It's this one. Well done. So just to recap, so when it's connected to a battery, remember I was talking about the proximal and the distal plates. So when the proximal plates voltage reaches a maximum, it's saturated and it stops transmitting any current basically because there's no voltage difference. Does that make sense? I mean, it doesn't, but yeah. Final question on this bit. Which of the following two statements best describe current and voltage in an inductor when it's connected to a battery? So does the voltage rise? Does the voltage rise and current fall? Do the voltage and current follow each other? Or current rises, voltage falls? Does the rate of rise of current fall as the voltage falls? Or does the voltage and current remain constant? And this is two statements that relate to an inductor. Shout out some letters. You might be right. So this is the one where a coiled wire creates a magnetic field around it and then creates an opposite voltage and equal opposite force. So the two statements best describing this are C and D, because as the current rises, it will create this electromotive force, which is an opposite force to what's flowing, so the voltage will fall. However, as I was saying, with it being like a negative exponential, the rate of rise of the current will also fall, because again, it's being opposed. Okay. One more, sorry. So another true false. So for A, let's do A. The ratio of the output voltage to the input voltage is inversely proportional to capacitance and frequency for an RC circuit. Is that true or false? It is true. B, the higher the frequency, the higher the ratio of output to input voltage. I think that is false because it's a low pass. Yes, because it's a low pass circuit. So the lower the frequency, the higher the output input voltage. The output waveform is the integral of the input waveform. Yeah, I think it's true. Yeah, that's the integral. The higher the capacitance, the higher the output voltage. I don't think, no, that has nothing to do with that. And finally, for a DC circuit, the output-input ratio would be 1. That is correct because for a DC circuit, the frequency is 1. So when you, oh no, the frequency is 0. Yes, because it's just a single current. So it would be 1. Cool. Moving on to amplifiers and interference. Why do I need to know about this? I asked myself this many times when reading about electricity. But it is kind of important because we want to know what the ideal properties of an operational amplifier are. And this is because we want to know when an electromedical signal is being faithful to what truly is happening in the patient's physiological reading. Also, obviously, currents or signals start off as an analog signal and they need to be converted to a digital signal, and this allows them to do that as well. And the sampling rate of the analog signal must be appropriate, otherwise we'll get something that doesn't really represent what's true in real life. So this is a diagram of an operational amp, and essentially, like the name, they're designed to amplify. So we talk about the gain of an amp, which is essentially how much the electrical signal is increased. They have the feature of having a very high input resistance, and this avoids drawing current from upstream. And another way of saying that is that it has a high common mode rejection ratio. And therefore, it's another way of neutralizing upstream circuit noise as well. So this is a differential amp. So as you can see, it has 2 inputs. One is a non-inverting input, so the sign will remain the same. And then the other one is an inverting input, which inverts the input signal sign. And again, that is a way of neutralizing any upstream noise. Because if it's common to both, it will be neutralized. So we can combine these with other elements, and then that also allows you to feed the output back into the input. And you can then use it within the other functions, so differential, integrator, inverting functions as well. So just to put, again, it back into a context of an ECG, this is a typical sort of the processing of the signal to finally appear on our computer at the end. So the ECG signal is first amplified by the differential amplifier. You may also have other signals that are coming through via a wheatstone bridge, which also allows you to filter out the noise, as we said before. And then it will go through the CR/RC filters, which allow only a certain range of frequencies to be amplified. So for an ECG, it would be 0 to 100 hertz, for example. And then there is an analog to digital converter, which basically, you don't need to know too much detail about that, but allows you to visualize it on a screen. So for example, the smooth waveform here would be the analog signal, and we take a sample from each of these points, and it essentially recreates that on a screen. And you can imagine if you didn't sample it often enough, you would get, like, for example, we did there, then there, then there, and it would look like a very different waveform to what you actually have. Cool. Quick knowledge check. So true or false to the following statements regarding why op amps have a high input impedance. So is it to reduce the input voltage, true or false? Just shout out. Again. So it basically, well, we'll comment into it. So is it to reduce signal distortion? Yes. No! What? Wait. Okay, no, I think that's incorrect because it reduces the current drawn in by the amplifier so that you don't degrade it, but it doesn't actually affect the signal itself. But it's a very confusingly worded answer, that one. So this one is correct because it reduces the current drawn in by the amplifier. D is incorrect and E is correct because it does not degrade the signal, but it doesn't really take anything away from it either. And then that's also incorrect. Well, I can actually look at those. You could do that anyway. Oops. So, and that's just one more, I think it is, another true or false regarding the purpose of a differential input of an op amp. So this is the one where I was talking about it having 2 inputs. and inverting and non-inverting. So is it to mathematically differentiate the input signal? No. Is it to invert the sign of one of the input signals? So I guess I'm going to sleep. That is correct. So you know it has an inverting and non-inverting one.
Yeah.
So one of the inputs will be inverted, and that basically gets rid of noise. To double the magnitude of the input signal, that is incorrect. To change the sign of the input signal, that is incorrect. I don't really know why, but it's to invert the sign of one of the input signals, not to change both. And then to cancel the effect of unwanted input signals, that is correct. So that's how it sort of, if it changes the sign for one of them and it's common to both pathways, then it will get cancelled out. It's quite similar to the wheatstone bridge idea, which is why it's very confusing. We've all heard of the wheatstone bridge. This is a stone bridge also. This is a wheatstone bridge. So what is a wheatstone bridge, or what is the purpose of a wheatstone bridge? Essentially, it is to reject noise signals. So an example of this would be in an arterial line, where obviously movement of the line and movement of the patient might produce noise. We obviously want that to be cancelled out. We only want to see the small, minute sensation on the screen. And it allows it to be detected and amplified, basically. So it's similar to what we were talking about before. So it is a type of voltage divider, but the structure of this circuit is basically a bridge circuit where the voltage dividers are connected back to back. And this means the bridge is balanced because there's no potential difference between these 2 points, X and Y. And therefore, no current would flow between them if they were connected. But with the wheatstone bridge, we put a transducer on one of these sections, which basically means that only the signal that's going through the transducer will cause a potential difference in the voltmeter. And any other high voltage signals which go down both arms, they'll be cancelled out. And so that's how it basically gets rid of noise. So an example of this transducer would be like the strain gauge diaphragm in an arterial transducer. You can also add another transducer to the other side if you wanted to make it even more sensitive. So key points. So this kind of looks kind of familiar, doesn't it? When you look at the arterial clip that you put by the side of the patient at the level of the heart. And that basically contains the wheatstone bridge. And it's a pair of potential dividers connected in parallel. It is a means of detecting any small potential difference between its parallel arms, and therefore any unwanted signals are eliminated. How are we going to sort of relate this to the patient, and which kind of tissues can be measured in terms of excitable tissues? So can anyone give me any examples of a biological potential or tissues in which an electrical impulse can be transmitted? Yeah. So heart, cardiac tissue, by ECG, brain signals, EEG, and the final one is muscle tissue, EMG. So when we look at analyzing these kind of biological potentials, they're again composed of sine waves, but they're in different frequencies. And the analysis that we use to sort of compose all of these different frequencies into a single one is the FRCA analysis. But the size of the measured potential does depend on a couple of things. So we know that when the heart is bigger, the size of the potential is larger. And so that's the excitable tissue mass. And also the amount of tissue separated from the heart from the electrode, which we know from obese patients with COPD. That will also dampen the signal. This is the EEG, which we have obviously seen on our BIS monitors. The EEG will measure the summed electricity in the brain. And depending on the area and the state of the patient, so are they asleep, are they wide awake, there will be a predominant frequency. So, the gamma frequencies, high frequency problem solving concentration is what it's related to. Whereas when we have someone with general anesthetic, they will generally have opioids being predominant, and that's a sleep dreaming state. And then there's the EMG. So skeletal muscle tissue does repolarize very quickly, and the activity is dependent on the number of motor units stimulated. So this frequency is a lot higher than that in cardiac muscle because of the short repolarization. As I mentioned before, defibrillators are a type of clever capacitor. So they collect and they discharge the electrical charge. And essentially they have features that make this more efficient, more safe, including the gel pads, which basically minimize the impedance when you apply the pedals, although we don't know if no pedals anymore. That's very, very dated, but we still obviously apply pads which have jelly on them, and that will minimize the impedance. Final example is nerve stimulators. So we've got a peripheral nerve stimulator here, which we typically put on the ulnar nerve, and that will transmit obviously the signal through the skin using gel electrodes. And then next to that we have a needle nerve stimulator. So this is the one that we might use for nerve blocks, and it's useful because we can measure how much voltage we need to stimulate the muscle. If it's incredibly low, then that probably means you're in the nerve itself, so you should not inject at that point. But essentially, you should need less and less of a voltage to actually get the neuromuscular junction to cause a contraction.